Okay, Epic Gamers, I'm ready. So let's see. Today a new paper came out. Actually, some guy's dissertation about a new module system for Haskell. And you know what? I've had a lot of issues with Cabal and whatever, so I'm really interested into this paper. So let's actually dive into that and start reading it and see what it is. What's it about? Maybe it solves all the problems. Maybe it does nothing relevant. But I've done some reading and it actually looked really interesting for what I've seen so far. So that's pretty good. Okay, cool. Let's get into it. Right, I forgot one. Let's just get started then, I guess. So the paper is called Non-Reformist Reform for Haskell Modularity. And they want to make a new module system without changing the language itself. So that's interesting, right? Like they're just gonna bolt on top and make everything work together, apparently. There's like a little abstract, we should probably read that. Think of it. So if you understand the abstract, then you know you're pretty far along on understanding the entire paper. I'm not sure if you can understand the entire thing from just the abstract because it's really fucking long. Hi Sky Bro, are you asleep again? What's up? We're reading papers today. Module systems like that of Haskell permit only a weak form of modularity in which module implementations depend directly on other implementations and must be processed independently order. In other words, like you could say one module would depend on the other by using import statements. That's basically what they're saying here. Okay, module systems like that of ML, on the other hand, permit a stronger form of modularity in which explicit interfaces express assumptions about the dependencies and each module can be type checked and reasoned about independently. So I think this means that you could like compile them independently as well. You don't need to have one module to reason about the other module. That's like what they're saying here. Been awake for like 2 hours. Are you still sick, man? You get better soon, man. Naturally, I woke up for this stream. Thanks! That's really cool. Oh, I'm happy. In this thesis, I present Backpack, a new language for building separately typed checkable. I'm still sick. That sucks, man. It sucks. A new language for building separately typed checkable packages on top of a weak module system like Haskell. The design for Backpack is the first to bring the rich world of typed systems to a practical world of packages via mix-in modules. I don't know what that means. But like, it's quite common for if you start reading a paper that you don't understand the abstract. That's like normal things. That's nothing to be concerned about. That's why it's an abstract. Like, this is for people that are deeply familiar with the field. I guess I'm not one of those people. That's actually something I am interested in. Dynamic linking for Backpack modules and multiple worlds separation. Wonder how much Backpack does really at it. What are we reading? We are reading that, like, this is a fresh paper from the printing press. I wanted to do an ancient paper, but I saw this today on Reddit and I got really interested in that. So it's basically this link. The guy just finished his dissertation on this thing. Scott Kilpatrick. I don't know if anyone knows that guy, but there you have the link. It was basically a Reddit post. But upvoted a lot as well, because I think a lot of people are interested in module stuff. Because it's a fucking pace. Yeah. And by pain in the ass, I mean like Cabal hell, right? We've seen that multiple occasions on this stream that I tried to do an upgrade and it just took me hours. Or, you know, like a couple of working days just to get continuing with the upgrade. And that was mostly because of the module system, I think. I don't know. But I suspect that's the case. So it's inspired by the Mix ML module calculus of Rosberg Dreyer. No idea what this is either. But by choosing practicality over expressivity, oh, that's cool. That's really nice that they choose practicality over expressivity. Both simplifies the semantics and supports a flexible notation of applicative instantiation. I don't know what it means either. Applicative instantiation. Do you mean like applicative as the type class? Probably not. Moreover, this design is motivated less by foundational concerns and more by the practical concern of integration into Haskell. So they try to actually make it work together with existing Haskell. That's what I'm getting from this. So there's like no big theory of unification going on or whatever. It's just like, okay, this will work with the existing Haskell stuff. Which is good, which is really good. The result is a new approach to writing modular software at scales of packages. The semantics of backpacks is defined via elaboration into sets of Haskell modules and binary interface files. Okay. This showing how Backpack maintains interoperability with Haskell while retrofitting it with interfaces. In my formalization of Backpack, I present a novel type system for Haskell modules and provide key soundness theorem to validate Backpack semantics. So what I'm concerned about is like, do I need to do much stuff to use Backpack, or is it like out of the box supported for us? Something like is this something that makes our life better without me having to do anything? That would be really cool. But I don't think that's the case. I think you actually need to do some descriptions. Or there's also German abstract. If anyone can read that, I can't. I think Lumi can, but we have it. Acknowledgement. We're gonna skip this because this is just him being thankful to everyone around him and being humble. I don't care about that. Yeah. Like the author of this thing actually got degree and everything out of it. So he moved up in life, I guess, into a next level. I don't particularly care about the author at all. I just care about the ideas he's presenting. So that's why I skipped that part. Okay. Spectre is haunting Haskell, the spectre of modularity. Specifically, the spectre is Backpack, a new extension to the classical Haskell compiler, GHC. We know that guy, right? And the Cabal package management system, and we definitely know that guy. Yeah. I don't know if you want to know this guy, but we do. We do. It's forced upon us. I thought you were sort of German, and that was something. Yeah, I'm like a swamp German. It's like, Germans come from the mountains, and Dutch people are from swamps. That's where we're born. Backpack addresses a long-time deficiency of the Haskell programming language and package ecosystem. Haskell lack of strong modularity, whatever that means. And he's gonna talk about it extensively. I've already read some of this to see if it's actually fitable for streaming. Need to explore this stuff, right? But it is, I think. It's easy enough to understand. I think the term applicative refers to ML notation of applicative versus generative modules. It doesn't help me. What is generative module? What is an applicative ML notation? Are you talking about the type class applicative? Anyway, Haskell lacks strong modularity, particularly at the level of separately developed packages. With Backpack's strong modularity, it's finally available in Haskell, and the entire Haskell ecosystem of packages stands to benefit from it. That sounds promising. There now exist new ways of expressing modular Haskell programs and libraries, with new potential modular static checking, new modular programming idioms, and hints at new avenues for development. Overall, Backpack is a leap forward for Haskell, but it's also a leap into the unknown. It sounds like, just regular Haskell things, I guess. Basically, generative means every instantiation of a module with arguments is distinct from everything else, whereas applicative modules would unify the modules with equal arguments. Sounds like Nix. I don't know actually if this sounds like Nix. I think this is actually tackling GHC module management directly. So Nix is like a layer on top of whatever Cabal is doing. And this may actually be a modification on both Cabal and GHC. I'm not sure. Wait, what does it say here? Specifically, a Spectre is Backpack, a new extension to the classical Haskell compiler and the Cabal package management system. So they modified both of them. Whereas Nix doesn't modify either of these things. It just builds on top of them. Which leads me to believe we can probably use, Backpack with Nix. Leap forward, but also leap into the unknown. Sure, it's not like 20 leaps backwards, and then maybe going forward. Backpack exists today as an engineered artifact. That excites the statement of my eventual caller, blah blah blah. Okay, there is some artifact available to use. Then they're talking about the title of pop-up paper, Backpack retrofitting in Haskell interfaces, convey the essential idea in Backpack of retrofitting the existing Haskell language with a new form of modularity. 20 leaps backwards, then going forward in a different direction. Yes! Maybe we wanted to go back all along. That's why it's called Backpack, by the way. You need to go the other way around. What do you want to do? Thought you loved Nix. I've started to dope recently. I'm sorry. Retrofitting refers both to building modularity on top of existing Haskell language rather than replacing it, and to research challenges of formalizing a module system for a real programming language that actually in use, Haskell, instead of inventing yet another ML-like system that only exists on paper. Well, that's cool. So I'm wondering, would this stuff, to use this stuff, do we need to change the way we're writing Haskell? or to use this stuff. I think this is what they're saying here. We're extending Haskell, and you need to write in a different manner, which would be annoying because then we can't use it for existing libraries. That's why I wouldn't. I'm not really sure. Okay, let's like order thing. Strong modularity, new GTC extensions, or new Cabal directive in order to maintain expressive. Weak modularity. If what is said there isn't completely clear, basically a module instantiation creates a new world every time it is instantiated. So generative would imply that its types are not compatible, whereas in applicative they are. Where do you even see that word generative? Did I read past that? He's just talking about. He's still talking about the abstract. Yes. Thanks for giving me a list of figures. That's amazing. No, this is the acknowledgement. We skipped all that stuff. There's a lot of text here. Module system like that of Haskell permit only a weak form of modularity. I don't know. Mixing modules. I did saw the word applicative somewhere, right? Oh, okay. Backpack both simplifies semantics and supports a flexible notion of applicative instantiation. So, would unify the modules with equal arguments. So yes, we have applicative, not generative. So we don't need to know about generative, I guess. Like you're just saying generative exists and explaining how that's different from, I guess like C++ would be generative because it's generating templates, not even modules. Okay, so this is like something special and important to this system. But that probably also has to do with the fact that the current module system is like weak and they want to make it strong somehow. And they go, there's like a chapter for explaining what that is. Let's see, did we read this? Yes, I think so. This is like talking about the previous paper, retrofitting backpack, and there were some holes in that. The controversy of the original paper's title. Okay, explaining the title. We already said this in the introduction. This is not a new. This is not something completely new. This is something building on top of something else, and like trying to not, change the way things are too much. So making sure that existing programs keep on working, I guess. I hope. Modularity is one of those concepts in programming languages that has countless definitions and continuation. An unconventional definition would be that it's a property of a programming system in which programs can be broken up into different components and defined and maintain their own abstractions. The latter part of the property is where the importance of the type system comes in. As per John Reynolds' classic definition, type structure is a syntactic discipline for enforcing type level of abstractions. Type structure is a syntactic discipline for enforcing levels of abstraction. In this thesis, I don't try to pin down a more precise definition of modularity. I do, however, cast some light on the different considerations of modularity in order to motivate the general approach of backpack, the strength and the scale of modularity. The idea behind these two attributes of modularizing is not to categorize the whole programming languages, but to understand and categorize the modularity offered by their constituent language features. What kind of modularity is offered by the Haskell modules or by Haskell package? How does that modularity differ from ML modules? My characterization of modularity in these terms helps distill the essential differences and pin down what's novel about backpack. So yeah, he will explain a lot about this if you didn't get this in one go. Strength will be done here, and then later will be skill. And this is like the difference between, defining modules in your programming language or, using Cabal to install packages from the internet. And strength is something else, which we'll be reading here right now. What makes programming languages have strong as opposed to weak modularity? I've hinted that the ML family of languages like Standard ML and OCaml offers the former, while Haskell and most other languages offer the latter. Boiled down to its essence, the difference is best captured whether there is any facility for abstraction over program components, typically expressed through signatures. The presence of such abstractions indicates strong modularity. In weak modularity, on the other hand, concrete program components may only depend on other concrete program components without any abstractions over the implementations. Okay, so Haskell has weak modularity and ML apparently has strong modularity, whatever that means. We don't know yet. The definition of standard ML perfectly summarizes strong modularity of the module system of SML. So this is an example. The principle of inferring useful structural information about programs is also represented at the level of program modules by inference of signatures. Signature describe the interfaces between modules and are vital for robust large-scale programs. When the user combines modules, the signatures disciplines prevent him from mismatching their interfaces. So this, like, sounds like types, but at module level apparently. By programming with interfaces and parametric modules, it becomes possible to focus on the structure of a large system and to compile parts of it in isolation of one another. We can't do this in Haskell. We need to compile lower level modules first, right? So if I depend on data to text, I need to compile data to text first before I can actually use it. And apparently you don't have to do that in ML. So that's the difference from what I understand. So if you could, like, split this up and make a strong module system, it probably means that you can compile in parallel as well, giving you faster compile times, which would be nice. Even when the system is incomplete. Yeah, so like, if some other module doesn't exist yet, because we programmed in our module against an interface, we're still fine. We don't need to make sure the other part is working. And to some extent, we can do this with functions in Haskell if we have a type signature, for example, and then use bottom type, but not at module level. This software philosophy has served the ML family of languages for decades. Signatures along the matching of implementation against them constitute a principal language feature in the module system of ML family, in particular SML and OCaml. They enable both client data abstraction, in which the parameterized module, also called a functor, and I think this is different from the functor we all know and love. This is something else. Uses a signature to abstract over the implementation of some other module it depends on. So we use the functor to say what we depend upon, the functor. And that's not a category theory functor, that's like something else. And the implementation side data on which the implementation, also called the structure, hides away or seals the particular details so that only the given signature is visible to the clients. So what we do is we describe what we want from the system in like functors, and then we make some implementation for that, providing a new interface which can be used by other modules. So we depend on some functors and then provide a new functor to the structure for other modules to depend upon. That's what I'm getting from that. Client-side data abstraction. For purposes of this thesis, this first use case of signatures, client-side data abstraction, that illustrates strong modularity, in particular in the ML family. Strong modularity comes in the form of functors. As an example, consider the following list-based implementation of a finite set of elements in SML. That's like standard ML, I guess. It's a functor set that abstracts over the type and structure of elements via the interface or the type. I don't know what this means. Apparently this is the functor, so this is like the type signature you depend upon or something, and you call it order type. A nice way to think about a module system is that it's mostly deferred linking, aka late binding, although this usually defers to linking time or module composition time and runtime. In that sense though, a late bound language is strictly more modular, and OOP virtual dispatch or airlines message passing is an example of late binding at invocation time. So you're talking about strong modules now. I guess like Java also does it with like class paths. You could just provide whatever implementations you want on a class path and it will kind of figure it out based on names. Yeah, okay. But not all ML variants support functors. For example, the popular, this is what he's talking about, right? You can't do this stuff in F# or CakeML, apparently. Both execute strong modularity for functors as part of their own technical trade-offs, resulting in weak modularity. Though considered weak, these languages nonetheless offer signatures and therefore implementator-side data abstraction. F#, I feel sicker again. I'm helping Skybro. They're saying that F# is doing it wrong. They're saying it's doing it wrong. It's not doing the fancy SML stuff. No. Bad F#. So like the paper is agreeing with you, Skybro. But then the other hand, the F# people get some other technical stuff in return for not doing it right. But that's cool. Like they get something in return. That's nice. Like it's not a complete loss for them. Too bad. It's usually like that, right? Like you trade some property for another property, and then you hope to profit from that. Though considered weak, these languages nonetheless offer signatures and therefore implement their side data abstraction. Their modularity is quite strong, but it's not fully weak either. In a world of weak modularity, modules cannot abstract away their dependencies. Implementations may only depend on other implementations. So this is what we do in Haskell. This is a pretty conventional view of modules. Each, also like, JavaScript and Rust or whatever. Each module defines some stuff. Partly by using that stuff, it imports from other modules. I guess like in C, it's interesting because you can specify what implementation you want to use. And you can also do like dynamic linking. So C may also be like strong. I don't know. I was thinking about reading that. You also have like header files. That will be your functor. A header file basically. So C doing it better than Haskell. There you have it. C better than Haskell. Some stuff partly by using that stuff that it imports from other modules. For example, consider a Haskell module called server that imports a socket data structure from another module called socket. With weak modularity, processing a module, e.g. type checking it, requires first processing the imported modules in order to understand the specification of what was imported. Because the imported modules must already exist in order to be so processed, there exists a rigid order in which modules may be processed. And that's why you don't really get good parallelism while building Haskell packages, because the bottom stuff needs to be done first before you can do stuff on top of that. So, you need to compile base first before doing anything else. And not the order of processing, but even the order of development. The downstream modules must be developed after the upstream ones. That's also a good point. In the example, developing and reasoning about server module can only occur after the socket module has been fully fleshed out and implemented. Well, you could like define data structures and all, but I guess like to them data structures is also implementation, because you only need to have like data as an interface, right? Webpack is a module system for JavaScript, by the way. The bundler allows you to override unwriting modules at linking time, but you can also do this at runtime. It's referring to strong modularity here. I know about Webpack. It's really interesting that they're using Webpack now for JavaScript, because now you have to compile your JavaScript code. I found it funny. Professional JavaScript developers. We are an interpreted language, but we need to use this compiler. But then they also can use like ES6, yes, and compile it down to crappy old JavaScript. In a strong modular system there would be a facility for expressing the expected interface of imported modules, with implementations of those modules linked into the program later, so that the module can be processed independently of the modules eventually linked. Server would instead depend on some socket interface that specifies the socket data structure, and only when the server imports is linked with socket, the program is considered complete. Another drawback to weak modularity is that the module cannot be reused with the same program by depending on related but different modules. Right, so this is where you get, in Haskell, if we changed one of the modules below, the dependency chain, we modify that, we need to compile everything that depends on that. That's like something we get, right? That happens all the time. Like, for example, if I change anything in a language, all the modules need to be recompiled. And what they're saying here is that if you had strong modularity, you don't need to do that. So I feel like this paper is maybe a way into getting faster compile times in Haskell. How about that? How can the server module be reused with different implementations of sockets? For example, to test against the mock implementation of sockets. Since dependency goes from implementation to implementation, there is no way to break it and move it into a different one. Aside from this standard notation of... So you would still have linking time, I guess. Linking time already is a pain in the ass, but... Aside from this standard notation of modules, weak modularity regularly occurs in another form. As packages in package management, in such systems, a package representation, a bundle of source files. That's, by the way, one of the reasons why Scala best package has changed from using cake pattern to weak modularity to using OOP wiring. Really? Dependency injection? They went to that? Cake pattern causes use compilation if anything's changed. Yeah. It's kind of interesting they went back to dependency injection. Back when I was using Scala, they were like, oh, you should use implicits for dependency injections. But yeah. With build time dependencies on other externally defined packages that bears a unique name and a version number. This system of structuring open source programs spans various software ecosystems. Wait, what am I reading? I forgot. It regularly occurs in other forms as packages in package management system. In such systems, a package represents a bundle of source files with build-time dependencies on other externally defined packages. That bears a unique name and a version number. Yes, this is what Nix does, right? Doing the package management like that. This system of structured open source programs spans various software ecosystems, from language agnostic systems like Debian's apt to system-specific, particularly for programming languages like Haskell's Cabal/Hackage. Or, you know, whatever you want, pip, whatever. Macro-based dependency injection, technically at compile time dependency injection. It just statically analyzes dependency graph and fills in the boilerplate. Okay, that's cool. So apparently you can also make Scala weak module. It's kind of weird that you can have both. You can make strong modularity and weak modularity in Scala, but in Haskell, we only have weak modularity. We have very strong weak modularity in Haskell. In Scala, there's choice, apparently. In package management system, packages are implementations that depend on other implementations. Weak modularity. Generally, this dependency is expressed as package named and range of version numbers. E.g., socketlib is bigger than 2.1. It's a dependency on package rather than series of packages named socketlib. But only those implementations marked as version 2.1 or later. Like, this is the issue we're having, like the fucking version bounds. So annoying. A package with this dependency must be built and linked against any such implementation version of socketlib. For internal entities defined in the package depend on entities defined in socketlib. While such version ranges appear to abstract over multiple implementations, thereby transcending weak modularity, they do not enable the independent development of the client package. If package my server version 1.2.3 depends on socketlib 2.1, because my server entity uses socketlib socket entity, then my server cannot be processed or built independently of a particular implementation of socketlib. Yeah, so you need to choose one. That's what I'm saying here. Even though there's a range you can choose from, you still need to choose. My language of strong versus weak modularity is intended to connotate the conventional distinction between strong versus weak typing in programming languages. With strong typing, one has stronger guarantees about the runtime behavior of a program, e.g. the absence of calling a function with the wrong type of argument. With strong modularity, one has stronger guarantees about runtime or even link time behavior of a module, e.g. the absence of linking a dependent component with wrong type of implementation. On the other hand, with weak typing and weak modularity, one has weaker guarantees. So, you know, stronger modularity is better, apparently. You get more guarantees because of strength. Okay. So do we understand? I think we understand strength correctly, right? We have weak modularity in Haskell because we get a behavior of we need to rebuild everything if we change something in the bottom. But in apparently you don't need to do this for OCaml because you have this stuff, this functor stuff. Right. So now the next one is scale of modularity, and this is also an interesting concept in that it's about package management. So the concept of programming large versus programming in small come from decades of folklore and vague generalities, a lot like modularity in types of literature. McQueen described the former as concerned with using modularity constructs for information hiding to impose structure on large programs, in contrast to the latter, which deals with detailed implementation of algorithms in terms of data structures and control structs. In this thesis, I adapt these concepts as scale of modularity, small versus large. Okay, smaller modularity. Modularity describes language constructs which capture fine-grained data abstraction. Water. Typically regarding the implementation of data structures and the enforcement of their invariance across abstraction boundaries. Oh, I lost it. Oh, there's another one. These constructs are referred to in the course of programming and its execution at the core level of a language, and in strong cases are reused, instantiated in multiple times in multiple distinct ways, with a top-level, fully closed program. Such constructs are sometimes considered unit of development, type checking, and reasoning. In languages with only weak modularity, the unit of development is taken to be the unit of compilation, as well. A unification of two granularities that refer to small rather than large modularity. Examples of small modularity include ML modules like the ones above, Haskell modules, Java classes and interfaces, C++ classes, and C source files, whatever. All these forms of modularity define and enforce data abstraction to varying degrees. In particular, in the case of Haskell modules, even though they have dual role of both reasoning and compilation, they are fundamentally part of data abstraction and the type system of the core of the language. So, the module system is defined in the language itself. We know that. Then you have like the layer on top of, so we have like the small modularity, which is like, the module keyword and that stuff. And then the other one, large modularity on the harder end, describes language constructs which aggregate the smaller constructs into a coherent whole that exists in a fixed form, a source code to distribute across systems. So this is like package management, right? Like this is Maven, this is Cabal, this is, getting dependencies from the internet. And if you read like a language tutorial, you will talk about this stuff, but you wouldn't talk about this. This is just something you have to know. This is like, you need to figure this out by yourself, usually. At this scale, modularity is more concerned with the organization of code dependencies and less concerned with the execution. Consequently, it's primarily domain, and this is also why you get like 10 different, like every language has its own little package management, right? Like, you have pip for Python, and you have Maven for Java, because they're opinionated about it in the large. It's primarily a domain of statics, semantics, and not dynamic semantics. Reuse instantiation in a single top-level fully closed program is limited. Such constructs might be considered the unit of distribution, authorship, or versioning of a language. Example of large modularity includes Haskell packages, OCaml interpretations, source files into modules, OCaml-C, and generally any package management system like OCaml's OPAM. The dominant form of modularity comes in the form of packages, as described earlier. Such systems have arisen out of the increased need for distribution repository of open source, modular interdependent components as software systems evolve into that direction. Large modularity cannot be described as merely a particular mode of use of small modularity. Essentially, the way of small modularity is expressed and abstracted does not conveniently match the use case of large modularity. The following discussion of abstraction barriers in sanitation and, in the case of strong modularity, fully functorized style provides weight to that claim. Wait, what? Large modularity cannot be described as merely a particular mode of using small modularity. It essentially the way small modularity is expressed and abstracted does not conveniently match the use case of large modularity. Since modularity is about organizing, defining, and maintaining abstractions, the abstraction barrier that describes them help illustrate the differences in scale. In small modularity and abstraction barriers delineates tight specification about abstract types and the invariants that operations enforce about them. In other words, data abstraction. What am I reading, man? Help illustrate the differences in scale. Circumscribe them. Help illustrate the differences. Okay. So we use the abstraction barriers to figure out what we're talking about. In small modularity, an abstraction barrier delineates tight specification about abstract types and invariants that operations enforce upon them. Okay, I see. So we use abstraction barriers to figure out if they're large or small. Yes. Instantiation. Oh, this is what Lumi was talking about before. In other words, data abstraction, think of the example of set functor in ML. The set structure, the body of the functor, depends on an unknown ordering structure, the parameter of the functor. There is an abstract barrier isolating the set structure from inside it. The structure knows only the interface of the ordering structure, order type signature. The abstract T and the invariant of the leg function is the total order on T. And from the outside the abstraction barrier, clients of the functor know only the interface of the set structure, the set signature, not its internal implementation, the representation of the operations in terms of list. To clients, the abstraction barrier enforces a certain invariance about the abstract set. For example, any value of type set only contains values of type alt and can be... I'm gonna read everything. How big is it? Oh my god, it's 250 pages. We're not gonna read everything, I think. Let's see, this is the introduction, I guess, right? Well, it's gonna take a while. And I'm already like getting kind of dazed. I don't think I can keep this up. I'm gonna read everything. Let's be tactical about this then. Like I wanted to read the introduction because it's usually... Oh, there's code. Why am I reading if I can read code? Okay. I think we got the gist of it. It's written in a pretty verbose style. Yes, and they're using a lot of big words. I don't know all the words. And I really don't like this either. They're putting their annotations below pages. I shouldn't do that. Bad. Let's see. Let's look at the index and let's just see what the fuck they did. Modularity in Haskell. I guess we're already kind of familiar with that, right? In modularity. This is describing what is modularity. And I guess this is like one of the bigger chapters as well. Scale of modularity. Oh, it's just skill. Abstraction barriers. Yeah, because we already read this, right? This is like set as an indication of what the barrier of abstraction is, I guess. Instantiation, other way to illustrate the distinction between small and large module is looking at how modular components are instantiated. Okay, like I think we got it. Is this just describing the examples here, but with a lot of words? Survey of modularity. Modularity in Haskell. Modules carve up large program into units of compilation and reasoning. Each Haskell source file defines a module, and modules are processed, type-checked, reasoned about, and compiled in the order of dependency on another. That makes them incremental modular development and weak modularity. Yes. Okay. We don't need to learn about Haskell, I think. That's fine. They're giving an example of Haskell as well. I think this is for people that don't know Haskell or something. You know, why would you read this if you don't know Haskell? But there you go. Well, I guess like maybe the grading teacher or something wouldn't know Haskell. Maybe. Probably also knows. So this, you know, this is just a quick introduction in Haskell. You know, just this piece of code. Just, you know, something some people take years to learn. You can do this in like one chapter. That's fine. Just quickly learn it. You'll be fine. Don't worry about it. Just establish a talk about the existing module system to explain how different work compute. Yes, I get it. That's why I want to skip it. But that the first part was interesting, I guess, and then it got boring quickly. I don't know. I just got distracted, I guess. Let's survey of modularity. Modularity in Haskell. Okay, modularity in ML. We already kind of read that as well, right? They have like their little implementations. That's this guys, I guess, and then you know the functors, which are not functors. The fake functors. Forms of modularity, recursive modules. This is not allowed in Haskell. Yes. Recursive modules generally require forward reference. Module variable that acts like a recursive reference in the body. You can do this in ML? That's pretty cool. First, however, we consider the simple case of a single recursive module that refers only to itself. The following module Arnit is a conventional natural number, but written in a recursive module in OCaml. So you can actually use recursive modules in ML. That's really amazing. Okay, let's actually see what they did. There's a contribution chapter. How about that? You can just read what they did. So far I've taken a step of describing modularity, partly through my own definitions, and partly through a survey of all the related forms and features of modularity that concern this thesis. My hope was to plant the reader into broader research tradition, multiple traditions in fact, so that she might better understand. I'm not a she, you're a she. No, you! The novelty of backpack. Here I summarized more definitely what novelty is, what thesis contributes. First, hazier terms of modularity and design, and then more precise in terms of formal technical content. Strong large modularity. Backpack is an extension to Haskell that supports strong modularity and separate modular development on top of Haskell weak modularity and incremental modular development. Like in the ML module system, Backpack relies on the notation of interfaces to establish that strong modularity. So you have to do something. That's what I'm getting from this. You have to do something. It's not like it's magical like we hoped before. No. You need to define your interfaces, thereby allowing implementations to abstract over their dependencies. As a language and type system of modular packages, Backpack exhibits large modularity similar to, but not more expressively than, other systems of compilation units. That means that modularity in Backpack is concerned with static organization of module according to their dependencies on abstract, coarse-grained components, rather than dynamic execution of code, or even the creation and enforcement of data abstraction in core levels type system. I don't know what that means. Let's read it again. Backpack exhibits large modularity, similar to, but more expressively than, other other systems of compilation units. That means that modularity in Backpack is concerned with static organization of modules according to their dependencies on abstract coarse-grained components, rather than dynamic execution of code. So this is what I'm getting from this is that Backpack is only concerned about, like, you know, cabal level stuff. It's not actually an attachment on top of the module system itself. Is that what I'm reading? Mm-hmm. Well, let's just see. Contribution to packages. Packages in Backpack are expressed with mixin-based language and type system. It characterizes their well-formedness and respects the underlying type system of modules and core entities. Backpack brings principled and formal approaches of type systems to the mostly unprincipled and informal world of package management. If that's the case, though, it probably does not support multi-world. I would assume that he, for example, would implement Backpack for base, and then, you know, you could just make contributions to whatever library you want to, you know, make backpackable. And as soon as you do that, you get like parallel building, basically, right? Because Backpack can do that. No, could it though? Would maybe we need to describe Backpack for. Maybe we need to describe Backpack per module, like it's a separate unit aside a module, describing the interface or something. I don't know. This addresses two practical problems with Haskell packages today. First, a package author can develop her package implementation with respect to abstract dependencies on other packages, EA with respect to type interfaces for those dependencies. Second, dependency hell can be mitigated through ordinary appeals to the package system. Or in Backpack, dependency hell is ruled out by the package type system exactly when it's ruled out by the underlying language type system. How about that? So if it compiles, it works. If it compiles, it works at module level, not fucking version bounds. Fucking version bounds. Like, it's all version bounds, all the way down. So that's what they're saying here. Like, if your types line up, it's fine. And 99% of the time, if I'm in dependency hell, it's not types lining up, it's Cabal being a pain in the ass. So that's like what I'm excited about. Like less hell. Backpack brings. So actually, this may be a big thing then. I think contribution to mixins. Backpack brings a fresh perspective on mixins, an area of programming languages that has seen some familiar usage in object-oriented language, but not attention in the types and modules research literature. A key idea in this thesis is that mixins offer perfect model for packages. To my knowledge, this is the first research effort to formally model packages as they're conventionally defined as mixins. By twisting existing ideas and notation, mixins allow packages. But didn't I use this? Wait. I used this. Backpack has already arrived. Backpack is real. Lumi, let me show you mixin in my codebase. If you don't like Prelude, you can just hide it. What's a Haskell? This is a mixin, right? You're seeing it here, right here. So, like, I'm using a different Prelude. I'm using Relude, and there used to be actually a package for Haskell that hit Prelude. So, Haskell no Prelude. I guess like base no Prelude. This was a different package altogether, just not exporting Prelude. But now we can use mixins to hide it. So that entire dependency is not. What does it do? Yeah, I'm depending on base and I'm hiding the Prelude module. So this no longer exists, meaning I can override it. So if I go to command circ Prelude, this is my new Prelude, and I'm just like using Relude, right? Re-exporting Relude, and overriding some other functions as well. It's a weird name for the functionality. It is. I'm not sure if this is the mixin they mean. Maybe this is some separate thing, some other feature. I don't know. But it looks like it has the same name. By twisting the existing ideas and notations, mixins allow packages with deeply nested dependencies to seamlessly link and share those dependencies without syntactic overhead of sharing constraints that are fully functorized. Idiom ML functors would require in the form of the model packages. Moreover, the recursive linking of mixin could enable entirely new forms of modular package development that aren't expressed in conventional package systems. Fresh perspective on mixins. So maybe it already existed? The design of backpack needn't be fixed to Haskell. The same approach could be applied to any language. Okay, yeah. Package not module level. Rather than supplanting the existing module system of Haskell, Backpack is designed at the level of packages for three key reasons. First, unlike the Haskell module level, which is part of the Haskell language definition, so you can't change this because you would be a revolution, and you don't want to be a revolution because then you need to change all the existing code. You don't want to do that. That's a lot of work. Probably it's starting to be impossible for Haskell to change all the existing code. Well, I guess I did it in Python, so everything is possible if you really believe. Python countdown. Leaving the module system larger as is, Backpack can reuse the existing tools at module level, e.g. mechanism for type checking and module implementation with respect to binary representation of another module interface. Scala is going that language now with Scala 3. New language and tools, automatic migration to new language. Yeah, Python had automatic migration. Didn't you know? There's like Py 2 to 3. You can automatically write your Python program from 2 to 3 with this program. And 15 years later, we still have Python 2 code lying around. So good luck with that. Good luck. The lesson we learned from Python is that engineers are really stubborn. Second, the large modularity of right. Did we read this? Simply, it's nowhere near as set in stone as the Haskell module level. So this is like basically confirmation of the idea we had before. It's modifying the package system rather than a module system. Because module system is set in stone within the language report, whereas the package system is, it's kind of implementation defined. So we can change that. Hooray! I think it'll be easier for Scala. It's tightly integrated into the actual compiler itself and can do it automatically during a build. We still lose a lot of the old code, I guess. I don't know. Maybe it works for them. Who knows? It will be interesting. It will be interesting too, because you don't see those. Like, this is a natural experiment, right? You don't often see these kind of things happening. There's only one way to test this out again and do it again. Like in history, they will call this a natural experiment. Python was a natural experiment of rewriting so much old code to a new version of the language. I don't think it has ever happened before like that. And this will be the second occurrence. So maybe it's different this time. Maybe they learned from history. Probably not. No, but maybe because they put it into the language itself in the compiler or whatever. Maybe that was the lesson they got from it. Some breakage. But they are working on fixing all the use cases. Yeah, they're not gonna fix all the use cases. You don't understand. People are always going to find a way to break it. Especially because this is a one-off task, right? It doesn't make sense to find all the use cases. The large modularity of packages in Haskell and elsewhere has remained largely unexplored by types research community. We completely ignore it. And they're talking about Cabal. So this is evidence of the fact that nobody gives a shit about Cabal. This is he's saying it. The research community doesn't give a shit about Cabal. It's therefore an interesting direction to take in its own right. Backpack expands to the principled reach of type systems into quite unprincipled and increasingly critical for modern software development domain of distributed open source packages. Yes, because every language already has a package system, right? Most languages actually have quite good package systems. Like pip, for example, is pretty fucking good. Cargo is really good. You're trying to fix that, which is props for you, man. Good job. Good job. I'm happy. More with that expanded research reach of types, a couple of particular problems with packages in Haskell today can be addressed in a more principled manner. A package author can develop her package implementation with respect to abstract dependencies on other packages, EA with respect to interfaces of those dependencies. And dependency hell may be mitigated through ordinary appeals to the package system. Right, we already read that. Third, although some wish to define and use ML functors within Haskell module system, it's unclear how they would integrate with other language features. So they didn't change the language at all. That's good. That's really good. It means you can use your existing Haskell code base with Backpack. Probably need to define more stuff though. Type classes in Haskell can be used to parameterize code over bundles of types and accompanying operations as functor does, although not nearly as expansive. Only individual values can be so parameterized, not whole modules. And similarly, the data abstraction offered by ML functors and opaque So type classes are a bit of a problem because they span across modules. If you define a type class anywhere in a module, and you import it from another module, it will be automatically, pulled in. All the instances will be pulled into that module, like magic. And there's no way to get around that in the language, because type classes are something that should be everywhere. All the use cases are HC files which look like Haskell and include interface. Wait, what? There are those HC files which look like Haskell and include the interface declarations. It's basically abstract data types, type classes, functions, type signatures, etc. Oh, this is what they're doing? Sure, that was some I wish to do. Right, we don't do that. I mean, there's like an opportunity to actually do this if anyone is audacious enough to try and implement this ML functor style now, because you already have this other stuff there, right? As like a language extension, it would be kind of interesting. It's sick. So this is Backpack. Yeah. Sick. So this allows you to depend on this. It's just type signatures. How do you get, for example, dynamic? Oh, there's data, but we don't know what it is. Like, we don't know the fields of it. How do you know the fields? Oh, you define this as functions as well, I think. Like, this is the fan function we all know and love. Updated to get an event out. This is it. You see those data declarations only show parameters right hand side. They're abstract. Yes, so there's no implementation. Only what happens with the types. We don't even define. Right, we even for the data we don't define any implementations. We just have names and how the names flow through the functions. Okay, is this Backpack? This thesis is first and foremost a design or even an ideological contribution, as a familiar saying as the field goes. With Backpack, I staked out a new corner of the design space for modular programming. With caveat aside, this thesis also presents the technical contributions. Yes, it's maybe an old version though, it's 3 years old repo. I think Backpack has been around for a while. He just finished his thesis, that's why we're reading it. You know how it goes, right? You write an implementation and then you spend a fuck ton of time just writing down the thesis itself. But it also happened for my master thesis. I spent more time writing the actual thing, the text, than making an implementation. Because, I'm faster at programming than actually writing text. I think that's what happened. The principal technical concept of module identity. Some prior type systems for modules included a notion of module identity, usually called structure stamps. But this thesis is the first to expand the notation. Okay, this is like some technical details. We're gonna skip that. And we're gonna go into design of Backpack. Yes. Now the modularity in the ML tradition and Haskell has been mapped out, it's time to dive into Backpack. The language supports strong, large modularity. So we already defined strong in that it's independent of dependencies. Completely independent, which means you can compile things at the same time. And large in that we're using package level stuff. So, you got your apt, you got your pip, you got your cargo. In our case, we have cabal. So that's what I'm talking about. As described in the introduction, but in the context of other languages, what does it actually look like in Backpack? In chapter 1, I attempted to answer that question with a high-level overview of Backpack and its feature, focusing on the package level interaction and the module level. Following this one, chapters 3 and 4 of this thesis, my aim with this organization is that most readers can absorb the design ideas of Backpack by reading part 1. That's what we want to do, yes. Well, a subset of those readers, part 2, the formalization of Backpack. That's an excellent idea. We're probably not going to read the formalization. And we're just going to quickly do design of Backpack. Plus struggle. Yeah. Probably going to skip 4 as well. We're going to do 2 and 3. Design of Backpack and making sense of Backpack. That sounds like a good idea. I don't know how many pages that are, but... Backpack is supported by GHC since 8.2. Not but supported by Stack. Oops. Yeah, probably only by Cabal. Well, if it's supported by Cabal, then Stack already gets it for free, right? Because Stack basically depends on Cabal. Okay. Figure 2.1 gives the syntax of Backpack. Package definition D gives a package name P to a sequence of binding B. The simplest form of binding a concrete... Wait, do they have imports here? They do have imports. Stack doesn't work with it, according to the author of Backpack and the open issue on Stack. It just doesn't work at all. Wait, what? That's a problem. That's a big problem. Like, I think a lot of people are dependent on Stack, but I'm not, so I don't care. Okay, so we have like a syntax tree thing. Yeah, it'll stifle adaptation for sure. I hope we will make an implementation for Stack as well. The code, yeah, that's actually a pain. But most library authors, they probably are familiar with Cabal, so they probably don't have any reason to do that. Think of it. Okay. Syntax. The code in the square brackets represents implementation, whose syntax is just that of Haskell module. Indeed, in practical implementation of Backpack, the term M might be realized name of file containing the module's code. However, note that the module lacks the header module M where, because the module name is given by Backpack's description. Use stack. You want to use stack. Is there an issue? That's a big deal. Maybe they're gonna implement it, I don't know. I think stack does this. We use Cabal to parse the Cabal file, but then resolve generic manually. Okay, so they're actually not using Cabal. I actually need to make their own implementation then. Here you have just a solution potentially fixing a big issue with current Haskell ecosystem, and then one of the most popular tools is not supporting it. Hooray! Great. Depressing. Okay. Package AB1 binds to two modules A and B. In the first module bound by A imports nothing and defines core value X. Second module bound to B. I'm not convinced it actually solves anything in and by itself. Yeah, though, like it would only be solved if actually people would make these files, I guess. If like a lot of libraries would do this, you could actually start using it as application in like your application, and get like no longer need to use like versions, for example. But even like, how do you like depend on some Backpack stuff? Because this is only providing like the interface, right? How would I say that I would depend on something like this? Haskell types encourage breaking changes. Yeah, but like from my own experience, I don't have issues with types breaking. I have issues with version bounds and dumb shit like that. And this is like the problem he said he's addressing with this solution in his contributions. So what I'm reading from this is that this is actually a proper solution for my dependency health, at least. Probably solve. Yes, but if that's solved, then I'm happy. I would be very happy. Okay. But the issue right now is that what I'm thinking about is that if stack is not implemented, then a few people would actually be encouraged to do this. I know how hard it would be to implement it. Maybe it's like a library? Maybe. The code in square brackets represents module implementation, so syntax is just that of Haskell module, chapter 7. Indeed, in practical implementation of Backpack, the term M might be realized as the name of a file containing the module's code. However, note that the module lacks the header module blah, because we already read this. Package AB bound to two module names, A and B. The first module bound to A imports nothing and defines a core value X. One is it imports nothing and defines a core value X. The second module bound to type B imports the first module and makes use of that X in Y. So these are actually also signatures. If you go to base, for example, no, not base. Does it already exist? For example, data T's. Let's look it up. Maybe they provide the signatures like this, because these imports should be then not imports for Haskell modules, but the name. Maybe they're like generated or something. Who knows? These. Reflex Backpack. I'm pretty sure it'll depend on actual modules rather than HSIG if they don't exist. Okay, so we have like a fallback mechanism then. Yeah. So it will be actually pretty big effort to make this all work and keep it consistent. Yeah, it needs to be implemented for all packages. That's what I'm saying. It's gonna be. But then you don't need to do any more versioning. How about that? Couldn't you have made this automatically? If you only want to depend on types. The module bindings in a package are explicitly sequenced. Each module can refer only to the modules bound earlier in the sequence. In fact, the binding should be interpreted as iterative building. Yes, it wouldn't be a problem if you could generate these files. Module bindings do not shadow. Rather, if the same module name is bound twice, the two bindings are linked. See section blah. A package repository consists of an ordered list of package definitions. Each package in the repository is only the packages that occur earlier in the sequence. To make use of those earlier packages, you depend on them. A package includes them using the include binding thus. No, this is what? This looks different than this. It's not doing package. It's just signature. So I'm not sure if the if this hsig is actually backpack. Let's just Google it. How would you use this stuff? This launch page for backpack, actively maintained by Edward as of January 2019. Backpack is a system of retrofitting Haskell with an applicative mixin module system. Been implemented in GC 8.2 and Cabal installed 2, but not supported by Stack. The documentation of for how to use Bat is a bit scattered at this point, but there's useful up-to-date as of 2019 references. So we already could use this before, I guess. Build of backpack using packages, for example. Unpacked containers. Versions? No versions. Signatures. Key. Oh, that's pretty cool. What is this? Unordered containers. Cabal. Key.h6. So it is this stuff. Signature key where import. Oh yes, we have it. It already exists. But nobody's using it. Backpack, a new system for mixing in release for GC. Although Backpack is closely integrated with Cabal package system, it's still possible to play around with TOIX using a new command GC Backpack. Play around with expressions. What? Linking a signature matching. Okay, I don't know. So I think you could just generate these signatures, right? You might have used some code using Backpack. Find signature implementation for strings. It's quite comprehensive. Signature string. Oh, this is like this is like some base stuff. You didn't do everything. It's not the same as what I'm reading here though. Package your lib. Include your lib. Maybe change the syntax. It solves all the problems except it makes it compile faster and the version bounds are gone. Two big issues are dealt with, but we need to write a lot of code for doing that. But solves in principle, I guess. Couldn't you just generate this thing? Generate backpack signatures. Built-in classes like a module signature is a type signature for a module, similar to HS boot files. Module signatures contain only type definitions and signatures and do not have any values binding. Yes. Well, test it first before claiming. It compiles faster claim. Well, you read it right. If you have a strong module system like Backpack introduces, you can compile in parallel, right? That's like the theory we just read. Well, you know, maybe we shouldn't believe the paper, but if you believe the author, then yes. In theory, it does enable it, but does it actually do it? Probably not. But you know, if you move towards the direction, from a library's perspective, you could at some point in the future have faster compile times. I don't know if they implemented that. I would assume they did. Who knows? Like he probably focused more on actually getting this language right and you know, trying to get it into Stack probably. I don't know. Epilogue. Let's actually look at the conclusion and future work. Come to think of it. Like, I think we got an idea of what a language is now. We need to make these signatures somehow, and we probably can generate them. Probably. Because we already have signatures everywhere, right? We can infer them. I think from the last blog post, he gave up on trying to support Stack. Oh, why? That has been a while. Yeah. I mean, it would be really cool to actually have a solution to version hell. The research project that led Backpack started with a question shared between Simon Peter Jost and Derek Dreyer. What if Haskell mixin modules a la mixin ML? Originally, that question sought mixin at Haskell's module level. Over subsequent years, the practical challenges of retrofitting Haskell with interfaces pushed the focus one level up, to the package level. The accumulation of the questions and solution experimented in a new kind of modularity in existing languages became Backpack. Over the course of my work developing Backpack for research project, I have brought the rich research tradition of type systems for ML modules into the world of Haskell, and the less robust research world of package management systems. Staked out an entirely new modular programming in practice, formalized the Haskell module system in all its complexity, and developed a novel methodology. Yeah, we formalized another part of Haskell, thank you. You know, Haskell is kind of formalized. Some part of it are formalized. Not everything, just some parts. And it's spread over a bunch of papers. So, thanks for that. I don't know if anyone cares about that, but you have it somewhere. You have a part of it. Another part of it is formalized. Excellent. Applied my modeling of type classes to verify the vast majority of wildly used Haskell packages in the wild obey the key world consistency property. But you actually tried it? You tried to make sure that this is correct? stated and proved a key soundness theorem that both guides a potential implementation strategy and validates the design. We already have it, right? It already exists. The conclusions one should draw from my work on Backpack can be categorized into those regarding Backpack's design, part 1, and those regarding its formalization. I see the key design conclusions of Backpack as twofold. First, since packages have become an ubiquitous part of modular programming practice, they deserve the same attentions that modules tend to receive. Primarily with the research, I don't think modules receive a lot of attention either. I think usually it's like a thing you bolt on top of your language, right? I'll just do whatever. But maybe I'm wrong about that. Primarily with research traditions and concept of types. Second, mix-in modules offer fertile ground for imbuing packages with the status of expression language with a type system, more so than ML-style functors do. Okay. While formalization of Haskell modules is certainly a technical contribution of my work, it takes away for the research community around Haskell aren't so certain. I have presented as a type system for Haskell modules that incorporates their possibly recursive nature, and in doing so I have established some conventional meta-theory around the core type judgments. Wait, what? You introduced recursive modules? The thing really is that many people consider this often as a solved problem. Objects can model modules quite effectively, and most popular languages have classes as objects. Yes, and then, for some reason they would still make namespaces. Who knows why, but it exists. Okay, let's actually see what he didn't do with feature work. That was the important one. My work on Backpack has formalized the bulk of Haskell features that concern modularity. However, a few features have remained unincorporated into Backpack. On top of additional Haskell features, there are a couple of aspects of formalization that deserve consideration. These are discussed below. Type synonyms and new types. One could straightforwardly extend Backpack with both type synonyms and Haskell new types mechanism for defining abstract data types. Wait, what? Both would be separate entities along with data types and values, with accompanying defined entities specs of core entities. They would be imported, exported, and recorded in the modules types just like data types and values. However, for compatibility with GHC, neither would be declarable abstractly in signatures, either by omitting the right-hand side. Type synonyms are different, though, as they violate two assumptions baked into the data types of Backpack and core language. First, the latter generate fresh abstract types. So new types are like a wrapper around the type, right? And you can unpack them and repack them. You probably can add them to Backpack. That's what he's saying here. I don't know how useful. I don't know why he didn't add it in the first place, because it's quite common to use. Type synonyms are not a big deal at all to add, because they're just aliases, right? It's not a big deal. New type is nominal. Not always. Not always. And the idea of this abstraction, the idea of nominality, it is always. No, because I read that part about coercion. You need to figure out if it's nominal. Where's the wall of text? Coercion. Using coercion. There you go. There you go. Crucible is two-parameter class that instantiates types of compiler that can invert the same representation. This class does not have regular instances, that they are created on the fly during type checking. Trying to mind it, nevertheless, it can be pretended that the following instances exist. First of all, the trivial base case, safe coercions. Oh, there's another paper. Oh, you lost your first. What happened? You're also no longer a Twitch Prime subscriber. Structural archive representational. Okay, let's quickly look this up, just to prove my point. It's coercible needs to, we need to coerce instances declaration. We need new type native. Notice that each instance unwraps just one layer. Wait, where is the, why do you need to make a type class if it's always representational? What the hell, man? That's the problem statement, I guess. Maybe it's in the introduction. Haskell has always suffered from the embarrassing difficulty. Suppose that the module HTML program wants to break HTML to data of lines. The crucial question becomes, what instances of coercible exist? Given a simple but non-obvious strategy expressed largely with familiar language of type Haskell. Adding safe coercions to the source language raises new issues that abstract types current. I don't know, whatever. I read it somewhere, probably not in this paper actually. Let's continue with use about identity as it carries distinct inhabitants. The whole point of backpack is to act over nominality, such that it becomes parameterized and first class. My question is like, if you would have a new type in your signatures list, how do you represent it at the moment in backpack back then? Because like if you pass a new type to some function, it shouldn't be the same as the underlying type. Because for example, the type classes attached to a new type can be different. They can have different interpretations. Okay, so you didn't do that. Excellent. Type families open. Oh, you didn't do type families either? It's an open definition of type level functions that can be extended to modularity. Type families introduce a whole new category of problems for the type system. A concrete example can be found in the so this is like not complete at all, this system. If you don't have type families, you might as well give up, I guess. I mean, like lots of libraries are not using this stuff. The only one I know of is actually Servant. Servant and Reflex for sure. And yeah, so those are the big ones, right? Formalization. Good development of shaping. My definition are just objects are validated by not by Bruce meta theory, but their pseudo formal resemblance to. Why didn't you do type families? That's probably why people aren't using it widely yet. Type classes weren't supported until recently either. Yeah. So if you don't like new types, is basically a no. You have to have new types. And they're saying that new types is possible. Type alias is not a problem at all because it wouldn't give a compile error, right? It's fine. Enforces global uniqueness for type family instances. Backpack's world describes static knowledge about type class instances with prop. Oh, this is why it took so long to actually do this paper, because he just had a bunch of stuff he needed to support, like type classes, and it just took a long time to figure out how to do that. And then there's like new types, and I guess he's thinking that new types is not used a lot, but it is used a lot, for sure. Like new types make type classes more useful. Then yeah. It's like a trick to get around the fact that you want to have another instance. You can make a new type. Backpack's world describes static knowledge about type class instances with its propagated implicitly downstream models, but there's no reason to limit that static knowledge to type class instances. Type family instances could also nicely fit in the world of framework. And since Backpack already imposes package level consistency, which has argued to be a modularization of global uniqueness, the uniqueness requirement necessitated by the type family instance would already be enforced. What left then is to support the resulting core level type computation that equality that type families introduce, perhaps using similar mechanisms that is needed to support type synonyms. The Backpack, okay, he wants to formalize it with Cork. Is he gonna do this actually? I wonder. Because it sounds like it's kind of incomplete for the scope of Backpack and modularity. Internal language metadata. Endings, okay, that's all fine. Conclusions and future work. Practical implementation of world semantics. Broader scope for Backpack and modularity. I don't know if you can do it. Maybe you should ask him. I think we did it. We did it, right? We did it. What are they saying about it? The original Backpack thesis was quite readable and enlightening. I'll be reading this as well. One question. The usual way of getting modularity in OO languages to count as weak, strong, according to that. Interesting. Wonderful. I can't wait to read this. Congratulations on your team. What is strong module system? No strongness. Really hard and complicated though. I think it mostly works on AI stuff now. I'm really curious if he'll continue on this. Yeah, I wanna know if he wants maybe like he got the degree. So like there's no more motivation for him to keep on working on this thing. I'm gonna ask him. I'm not sure about Backpack existing. How does Backpack exist? A good question. Backpack today should be seen in two different ways. First, a representation of the syntax and semantics in terms of abstraction barrier between compiler and package manager found in Edward Young's thesis. This is the formal definition of Backpack today. The second, there is the engineered artifact that integrates Cabal and GHC tools. This is the programming fashion definition of Backpack that exists today and was developed in tandem also by Edward with the formal definition. Formal gives meaning and a more theoretical basis for the latter, but the latter is what Haskell actually interact with. I can say a bit about how my Backpack, let's call it Backpack 19, differs from the first notation, what Backpack is. The two research projects differ in there are two of them? Wait, so it is actually different. This is why the syntax looks so different from the signature files, I guess. It's different. Design of Backpack, it looked different, right? already said it. It looks different, but I didn't pay attention to it. Because I saw code and I was like, just, oh, I'll just believe the code. Man, don't you love research quality tools? I could, like, yes, I do love this. Why are the two? Why didn't you just rename it? Frustration incoming. Yeah, let's read and enjoy the world of research. I can say a bit about how my backpack, let's call it backpack 19, differs from the first notation of its backpack is. The two research projects differ in their goals. Mine set out to integrate the idea of mixing modules into Haskell as a new form of modularity and to present a rigorous formal development. While Edward's goal was to provide a formal basis to guide the concepts and implementation of an actual system. So you didn't even make a system. I think we both have a great respect for what the others set out to do. And while our PhDs overlapped, we ended up collaborating on how the things expressed and defined. So, like, there's nothing, like, everything is Edward's work. You're not doing anything. Is that what I'm reading here? What? Did we just read the thesis for nothing? Why is it so upvoted so much? We should downvote it. What the hell? Did I just waste my time? I think I just wasted my time. Detailed comparisons, you can see effective dissertations in Butters, Popple to the representation of backpack tests in backpack 14. In section 10 of his thesis, he discusses the differences between our spins on backpack concepts. I mentioned in my post that backpack 14 lacked any type class instances. I discussed the differences between my backpack 19 and backpack 17 as a more recent work. I would encourage anyone interested in the differences to read. Wait, maybe he did make an implementation. I don't know. I got the impression he actually did. Provides the original formalization of backpack and integrates type classes and properties into the formalization. A notable gap in a Popple. Okay, so like that's your contribution. You added type classes. Okay, so there's like another guy doing PhD on this. So there is work being done on this actually. Like there was some guy that did the initial backpack and got it into GHC, and now there's working on top of his work, making backpack even better. So maybe in the future we'll have like new types in it as well, and it maybe become useful at some point. But I want to ask if he actually made an implementation. I don't think he did. Oh yep, you have target on wall. This is like my shooting achievement. I was proud of it. They were all in the little black thing. From like it was like long distance. It was like 50 meters or something. What's up, mate? Fresh Daily. How are you doing? We either wasted our time just now or got a good observation. I'm not sure at this moment. So like yeah. This guy iterated on top of backpack, I think. And maybe he also made a contribution to GHC? Maybe? Let's actually look it up. He has contributions, right? Contributions. Technical contributions. Formats to design are eventually as familiar saying the field of code with backpack as state of the new core in design space. You formalized it. Maybe you just formalized it. Elaborators on the semantics of backpack. I don't know. Semantics of backpack to explain Haskell modules. The formal implementation. This elaboration offers a formal implementation of backpack that illustrates the essence of the idea. To compile away into straightforward model of Haskell plain modules. I think it's just a formalization. Then maybe they still need to do the implementation. Okay, this was a waste of time. I'm sorry, guys. I'm sorry. Thanks for watching, everyone. I suppose. We learned about backpack. It's not complete. And there may be an implementation around, but that's ancient and doesn't support type classes. So, yes, good. It does seem to solve problems I'm having right now. But this will probably take, another thesis to actually implement. Maybe someone else will do that. Who knows? This will make hell less painful. Upgrade hell. But it doesn't exist, I think. I don't know. Anyways, thanks for watching, everyone. I'll be back tomorrow and we'll be doing an open source stream, actually making code and doing a proper, making a proper project. What Haskell subreddit is? Oh, sorry. I'll show it again. Wait. This is just Haskell. Our Haskell. I'll send you the link. Wait. Yeah. So I was wrapping up, right? Tomorrow we'll have an open source stream and actually make code. Make code and we'll do automated video editing again, I think. Maybe we'll also do NIM, I don't know. One of the two. I think actually not NIM, because he made the live update, so we don't have to do that. Will be frustrating as well. No, we'll do something else. Not frustrating, we'll do something cool. Do something in Haskell, yeah. It'll be amazing. Let's do that. But thanks for watching, everyone, and see you guys tomorrow.